All right, let's look at some of the information necessary to complete Lab 9. So the link that's provided in Blackboard takes you to simulation here. We have a couple of different options and we want to pick the first one. So we will be dealing with water and iron, and then it will be helpful to know the temperatures of these things. So we can move these thermometers around. Um, Actually, let's do it this way. I'll put this one as far out as I can and this one as far in as I can. And that's going to make the one of the next steps a little bit easier. Okay, so the first thing we want to do is we want to figure out room temperature. If all of these things are just sitting here, then they should all eventually reach equilibrium and all be room temperature. So looking at the markings on any of these thermometers, the first mark at the bottom is a little bit hard to see potentially, depending on how big of a screen you're using. But then the second mark here, this is just a tad bit under that. Now, to make this a little bit easier to calculate, I'm going to say that this corresponds to roughly 77 degrees Fahrenheit. Even though it's a little under, it's hard to read, but that's what we're going to use for our conversion just because it makes a cleaner number. So if I want to find the Celsius temperature that this turns into, then excuse me, I want to keep in mind that this is going to be whatever Fahrenheit temperature I've got minus 32, and then technically multiply 5 over 9 in front is what you normally see with this, but a little bit easier on your calculator. Just take that answer and divide by 1.8. What you want to remember from that is that we have to follow our order of operations carefully. So don't forget that you want to handle the stuff inside the parentheses first. Okay, so we'll have 45 from that difference, and then divided by 1.8 is going to give us the temperature in Celsius here is 25 degrees. So even though 77 would be a bit warm, I think for most people for room temperature, 25 degrees Celsius is a cleaner number to be dealing with. Okay, then that's important because we want to use that information and we need to basically calibrate this thermometer. We want to see what the different lines are. So far it looks like that second line there, the first one above the bottom, appears to be about 25 degrees Celsius. And let's see if we can explore that a little bit further and confirm. So if I use my magic ice bucket, then you can see now that I've lowered the temperature of the water and it's much colder than the other things around it. This got down to the minimum bottom here, so it cools down to the first mark. Now, if we think about this, it makes sense that there's a minimum temperature for water, because under normal circumstances, if water gets beyond a certain temperature, then it will freeze and it will turn into ice. So because these are ice cubes at the bottom, I guess, I think that's what they're supposed to be, then the water can only be cooled down to ice temperature. So that appears to be 0 degrees Celsius. On the other side of things, if I use the fire to warm this up, then now you can see that the thermometer is rising. So it's now passing the third mark, keeps going, it's approaching the fourth mark, it's still going, and then it's getting now to the fifth mark, and then now it won't go up anymore. You can also see that they've added a little touch here, that there's steam coming off of the water. So this maxes out at the fifth mark, which appears to be 100 degrees Celsius, because if water got any higher than that, then it would boil, it would turn into steam, and it wouldn't be water anymore. So now we have a range for where we see water will exist on this thermometer. Using that information, the boiling temperature was at the fifth mark, the freezing temperature was at the first mark, and so there's 4 divisions between those. Okay, and then taking that a step further, there's 100 degrees of temperature separation between 0 and 100, spread over 4 different sections on the thermometer, and so that tells us that each mark then counts for 25 degrees Celsius. Just to confirm, that would mean the bottom one was 0 degrees Celsius, the next one up will be 25 degrees Celsius, which is what we said for room temperature, then 50, 75, and then 100, which is where this maxed out, so it matches our expectation. All right, good. So now we know each mark on the thermometer is 25 degrees Celsius. Now we need to check on the beaker. So The beaker is 3 liters, and we can tell that, not by the numbers, but by the markings that are here. So, every fifth marking is a slightly longer line, and just from real beakers and how they're marked, that's typically going to be a larger division. So in this case, we'll say that those are liters. If we count all of the lines on here, again, the longer ones are every 5, so we can use that to make this a little bit faster. But here's number 5, here's another 5 to be 10, and another 5 to be 15. And technically, you could go a little higher than that to get to the lip, but as far as where we can measure, it goes to 15 lines. Then we can use that to our advantage, because if this is a 3-liter beaker, then 3 liters is the same as 3,000 milliliters. And if we divide that by the 15 marks, then that means that every individual spacing between the marks is 200 milliliters. And we can use that now to figure out how much water is in here. So 5 marks is here. It doesn't quite get to 10, so we'll count individually now. 5 marks, 6, 7, 8. So this gets to the 8th mark. We want to remember that these are 200 milliliters per mark. So 8 times 200 tells us that we have 1,600 milliliters of water, which is great. Then water is very nice. Water is used as the reference point for several things in science and in the metric system in general. And so because water has a density of 1 gram per milliliter, if we have 1,600 milliliters, then technically we would take and multiply that by 1, because that's the conversion, if you want to call it that. And that means that 1,600 milliliters will turn into 1,600 grams of water. So again, water is the baseline, so conversion between mass and volume for water in these units is very, very easy, basically free. Okay, so now we want to turn our attention to the iron block, and then eventually we're going to mix these together. I suppose we're doing that now, aren't we? So we have this iron block. We can't really stick a ruler to it and find dimensions. We don't have a way of putting it on a scale. So what we can do is we can take and we can drop it in the water. Okay, so the water level increased. So if you just read the lines, you pay attention to nothing else, then all of a sudden it seems like the water level has gone up to the 12th line. But remember, that difference is going to come from the iron displacing the water, and that's going to allow us to figure out how big the iron block is. Okay, so 12 lines, and each line is 200 milliliters. Means that we would have 12 times 200, and we can see that now the water level appears to be 2,400 milliliters. Knowing that we have actually only 1,600 milliliters of water in here, then we can find that difference, 2,400 milliliters minus 1,600 milliliters, to give 800 milliliters for the size of the iron block. And I know it feels a little bit weird to think of a block being measured in milliliters, because we think of that as being fluid capacity. But keep in mind that milliliters are exactly the same as cubic centimeters or cc's. They're all set or defined to be the same as each other. Once we know how big the block is, it's 800 milliliters, we can actually use that with the density of iron, and we can find the mass. So let's clear some space, and then we can do a quick conversion there. The density of iron from the source I looked at is 7.875 grams per milliliter. And so we can use that to our advantage. Our original formula, we've got density is equal to mass over volume. If I put this side over 1, so it looks like a proportion, I can cross multiply, and I can find out that mass is equal to density multiplied by volume. And the order there is not super important. I just want to plug in the information. The volume we found first was 800 milliliters. I'm going to stick that over 1 so that it looks like a fraction. Then the density of 7.875 grams per milliliter. I'm going to say grams per 1 milliliter so that it stacks better. And then we see milliliters canceled. That's going to give us grams. And then multiplying those will give us 6,300 grams. So we can see the mass of the iron is a lot higher than the mass of the water, but that makes sense because iron's a lot more dense. Okay, so now we want to run our calorimetry experiment. We're going to take the water and we're going to cool it all the way down. So that's going to be 0 degrees Celsius. Unfortunately, it won't stay there. So I'm going to cool it down, then I'm going to heat up the block, and then I'm going to cool the water down, and we're going to kind of work it back and forth to be as consistent as we can. So according to the instructions, I want to come up to the 9th mark. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I want to go to here. So I'm actually going to heat a little bit past that so that it can cool down slightly while I'm adjusting the water. So I'm going to bring this back down. Then I'm going to take the block. I'm going to hover over the water until it hits that line out there, and then I'm going to mix them. So notice the iron drops temperature very quickly. The water only comes up a little bit, and we end up somewhere a little bit above that 3rd mark. Now, the marks themselves, remember this is 0 Celsius, 25 Celsius, and 50 Celsius, and it's continuing to cool down, but it was a little bit above that mark. So a little bit more than 50 degrees could be, say, 60 degrees, because unfortunately we can't see very much more clearly than that. But that is enough information for us to work through one of our giant formulas from lecture. So let's try that here. Remember that the heat that is lost by the metal is going to flow into the water. So that's why they're both changing temperatures, but in opposite directions. And we assume that that's being conserved and it works reasonably well. So we can take our MC delta T formula for the heat lost from the metal. We can set it equal to the MC delta T formula for the heat gained by the water. Where we've got to be a little bit careful here, so we need to make sure the change in temperature is going to be positive on each side with the way that we've got this set up. We don't want negative answers to anything. Okay, so looking at the information we have so far, we've got 6,300 grams of iron. Then the specific heat of iron, we're pretending right now that we don't know, so we'll just put X. And the change in temperature, because we were up at the 9th mark, which remember is 8 marks above 0, that's going to mean that we started at 200 degrees Celsius. And then our best guess for the final temperature is something around 60, so that's the best we can do there. As it turns out, this works reasonably well, so I'm happy with that. From before, we had 1,600 milliliters of water, which remember, because water is nice, is also 1,600 grams of water. And then water is used as a definition of calories, so its specific heat is 1 calorie over grams and degrees Celsius. Okay, so the change in temperature of the water, again, we want to make sure that this stays positive. So we're going to put the final temperature first, 60 degrees Celsius minus the original 0 degrees Celsius. We have a lot of units that we can cancel from this. The grams can cancel from both sides. The Celsius can cancel from all these parts. And all that's left over are these units from the constant. But that makes sense because the units from the water constant and the units from the metal constant should be the same units. So that's good. I basically just want to work through numbers for the rest of this. If I start to simplify, the right-hand side is a little bit easier to deal with. 1,600 times 1 is going to be 1,600. And then 60 minus 0 is going to be 60. And then we can finish this side out, I suppose, but that's going to give us 96,000. Then on the left, not quite as clear because we have a variable involved, but still we can simplify in a similar way. 6,300 times x is just going to be 6,300x. Then 200 minus 60 is going to be 140. Then if we multiply those together, we're going to have 882,000 times that x that we still don't know. Then from here, if we want to solve for x, then we want to divide by that number to make it go away. Because this is a metal, it should be a small decimal answer. So don't panic if it's a weird 0.0 something, 0.1. That is actually proper here. So running this through the calculator, we get something like looks like 10884, blah, 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 blah. So 0.109 if we round that to 3 places like we have from the textbook. And speaking of the textbook, if we go and we look up the value for the specific heat of iron, the book says that it should be 0.108. which means it is very, very close, less than 1% error for this simulation. So our estimations for where the lines are and how the temperatures move must have been very, very close to correct. And that's it.